Okay. Hi everyone, and welcome to the first installment of What's Up With That, the series that demystifies all things Chrome. I'm your host, Sharon, and today's inaugural episode will be all about pointers. There are so many types of types. Which one should I use? What can possibly go wrong? Our guest today is Dana, who is one of our base and C++ owners and is currently working on introducing Rust to Chromium. Previously, she was part of bringing C++ 11 support to the Android NDK and then to Chrome. Today, she'll be telling us what's up with pointers. Welcome, Dana!
Thank you, Sharon. It's super exciting to be here. Thank you for letting me be on your podcast thingy.
Yeah, thanks for being the first episode. All right, so let's just jump right in. So when you use pointers wrong, what can go wrong? What are the problems? What can happen?
Okay, so pointers are like a big cause of security problems for Chrome, and that's why we mostly think about when things go wrong with pointers. So you have a pointer to something, like you have a pointer to a goat, and then you delete the goat and you allocate some new thing, a cow, and it gets stuck in the same spot. Your pointer didn't change. It's still pointing to what it thinks is a goat, but there's now a cow there. And so when you go to use that pointer, you use something different. And this is a tool that malicious actors use to exploit software like Chrome in order to gain access to your system, your information, etc.
Yeah, and we want to avoid those. So what's that general type of attack called?
So that's a use after free, because you have freed the goat and replaced it with a cow, and you're using your pointer, but the thing it pointed to was freed. There are other kinds of pointery badness that can happen. If you take a pointer and you add to it some number, or you go to an offset off the pointer, and you have like an array of 5 things, and you go and read 20 or -2 or something, now you're reading out of bounds of that memory allocation, and that's not good. So these are both memory safety bugs that occur a lot with pointers.
Today we'll be mostly looking at the use after free kind of bugs. We definitely see a lot of those. And if you want to see an example of one being used, Dana's previously done a talk called Life of a Vulnerability. It'll be linked below. You can check that out. So that being said, should we ever be using just a regular raw pointer in C++ in Chrome?
Right. So, okay, so first of all, I think let's call them native pointers. You will see them called raw pointers a lot in like literature and stuff, but later on we'll see why that could be a bit ambiguous in this context. So we'll call them a native pointer. So should you use a native pointer? If you don't want to use after free, if you don't want a problem like that, no. However, there is a performance implication with using smart pointers, and so the answer is yes. The style guide that we have right now takes this pragmatic approach of saying you should use raw pointers for giving access to an object. So if you're passing them as a function parameter, you can share it as a pointer or a reference, which is like a pointer with slightly different rules. But you should not store native pointers as fields and objects, because that is a place where they go wrong a lot. And so you should not use a native pointer to express ownership. So before C++ 11, you would just say, this is my pointer, use a comment, say this one is owning it. And then if you wanted to pass ownership, you just pass this native pointer over to something else as an argument, and put a comment and say this is passing ownership. And you just kind of hopes it works out. But then it's very difficult. It requires the programmer to understand the whole system to do it correctly. There's no help. So in C++ 11, the type called std unique putter was introduced, and this is expressing unique ownership. That's why it's called unique putter. And it's just going to hold your pointer, and when it goes out of scope, it gets deleted. It can't be copied because it's unique ownership, but it can be moved around. And so if you're going to express ownership to an object in the heap, you should use a unique putter.
That makes sense, and that sounds good. So you've mentioned smart pointers before. Do you want to tell us a bit more about what those are? It sounds like unique pointer is one of those.
Yes. So a smart pointer which can also be referred to as a pointer-like object, perhaps as a subset of them, is a class that holds inside of it a pointer and mediates access to it in some way. So unique pointer, or mediates access by saying, I own this pointer, I will delete this pointer when I go away, but I'll give you access to it. So you can use the arrow operator or the star operator to get at the underlying pointer, and you can construct them out of native pointers as well. So that's an example of a smart pointer. There's a whole bunch of smart pointers, but that's the general idea, right? I'm going to add something to what a native pointer is while giving you access to it in some way.
Yeah, that makes sense. That's kind of what our main thing is going to be about today, because you look around in Chrome, you'll see a lot of these wrapper types, right? It'll be a unique pointer and then a type, and you'll see so many types of these, and talking to other people, myself, find this all very confusing. So we'll cover some of the more common types today. We just talked about unique pointers. Let's talk about absol optional next. So why don't you tell us about that?
Okay, cool. So that's actually a really great example of a pointer-like object that's not actually holding a pointer. So it's not a smart pointer, but it looks like one. So this is this distinction. So absol optional, also known as stood optional if you're not working in Chromium, and at some point we will hopefully migrate to it. Stood optional and absol optional hold an object inside of it by value instead of by pointer. This means that the object is held in that space allocated for the optional, right? So the size of the optional is the size of the thing it's holding plus some space for, you know, a presence flag. Whereas a unique putter holds only a pointer, and its size is the size of a pointer, and then the actual object lives elsewhere. So that's like the difference in how you can think about them. Otherwise, they do look quite similar, right? Like an optional is a unique ownership because it's literally holding the object inside of it. However, an optional is copyable if the object inside is copyable, for instance, right? So it doesn't have quite the same semantics, and it doesn't require a heap allocation the way unique pointer does, because it's storing the memory in place. So if you have an optional on the stack, the object inside is also right there on the stack. That's good or bad, depending what you want. If you're worried about your object sizes, not so good. If you're worried about the cost of memory allocation in free, good, right? So this is the trade-off between the two.
Okay. Can you give any examples of when you might want to use one versus the other? Like you mentioned some kind of general trade-offs, but any specific examples? Because there have definitely been, I've definitely seen use cases where unique pointer is used when maybe an optional makes more sense, or vice versa. Maybe it's just because, you know, someone didn't know about it, or it was chosen that way. Do you have any specific examples of?
Yeah, so like, okay, so one place where you might use a unique putter, even though optionals may be the better choice, is because of forward declarations. So because an optional holds the type inside of it, it needs to know the type size, which means it needs to know the full declaration of that type, or so the whole definition of that type. And a unique pointer doesn't, because it's just holding a pointer, so it only needs to know the size of a pointer. And so if you have a header file and you don't want to include another header file and you just want to forward declare the types, you can't stick an optional of that type right there because you don't know how big it's supposed to be. And so that might be a case where it's maybe not the right choice, but for other constraining reasons you choose to use a unique pointer here. And you pay the cost of a heap allocation and free as a result. But when would you use an optional? So optional is fantastic for returning a value sometimes. I want to do this thing, and I want to give you back a result, but I might fail. Or sometimes there's no value to give you back. Typically before C++, what are we on now? Was it given 14? I'm going to say it wrong. That's okay. Before we had abseil optional, you would have to do different tricks. So you would pass in a native pointer as a parameter and return a bool as the return value to say, like, did I populate the pointer? And like, yes, that works, but it's easy to mess it up. It also generates less optimal code. Pointers cause the optimizer to have troubles. And it doesn't express as nicely what your intention is, right? Return this thing sometimes, right? And so in place of using that pointer plus bool, you can like put that into a single type, return an optional. Similar for, holding something as a field where you want it to be held inline in your class, but you don't always have it present. You can do that with an optional now, where you would have probably used a pointer before, or like a union or something, but that gets even more tricky. And then another place you might use it as a function argument. However, that's usually not the right choice for a function argument. Why? Because the optional holds the value inside of it. Constructing an optional requires constructing the whole object inside of it. And so that's not free. It can be, arbitrarily expensive depending on what your type is. And if your caller to your function doesn't have already an optional, they have to go and construct it to pass it to you. And that's a copy or move of that inner type. So generally, if you're going to receive a parameter, maybe sometimes, the right way to spell that is just to pass it as a pointer. Because a pointer, a native pointer, right, which can be null when it's not present.
Okay, cool. Hopefully that clarifies some things for people who are trying to decide which one best suits their use case. So moving on from that, so some people might remember from a couple of years ago that instead of being called Absol optional, it used to be called base optional. And do you want to quickly mention why we switched from base to Absol? And you mentioned even switching to standard optional. Why this transition?
Yeah, absolutely. So as new C++ standards come out, we want to use them, but we can't until our tool chain is ready. What's our tool chain? It's our compiler, our standard library, and unfortunately we have more than one compiler that we need to worry about. So we have like the NACL compiler. Luckily we just have Clang for the compiler choice that we really have to worry about. But we do have to wait for these things to be ready and for a code base to be ready to turn on the new standard, because sometimes there's some non-backwards compatible changes. But we can forward port stuff out of the standard library into base. And so we've done that. We have a bunch of C++ 20 backport. We have a bunch of C++ 20 backports in base now. We had 17 backports before we turned on 17. Now they should hopefully be gone. And so base optional was an example of a backport, while optional was still considered experimental in the standard library. We adopted use of absil since then, and absil had also essentially a backport of the optional type inside of it for presumably the same reasons, right? And so why have two when you can have one? That's a pretty good rule. And so we deprecated the base one, removed it, and moved everything to the absil one. One thing to note here, possibly of interest, is we often add security hardening to things in base. And so sometimes there is available in the standard library something, but we choose not to use it and use something in base, or in absil, but we use it in base instead, because we have extra hardening checks. And so part of the process of removing base optional and moving to absil optional was ensuring those same security hardening checks are present in absil. And we're going to have to do the same thing to stop using absil and start using the standard one. And that's currently a work in progress.
Okay, cool. So let's go through some of the base types, because that's definitely where the most of these kind of wrappery types live. So let's just start with one that I learned about recently, and that's a scoped ref pointer. What's that? Okay. When should we use it?
Absolutely. So scoped ref pointer is kind of your Chromium equivalent to shared pointer in the standard library. So if you're familiar with that, it's quite similar, but it has some slight differences. So what is scoped ref pointer? It gives you shared ownership of an underlying object. And it's a smart pointer. It holds a pointer to an object that's allocated in the heap. When all scoped ref pointers that point to the same object are gone, it'll be deleted. So it's like unique pointer, except it can be copied to, add to your ref count, basically. And when all of them are gone, it's destroyed. And it gives access to the underlying pointer in exactly the same ways. Oh, but why is it different than shared pointer? I did say it is. Scoped ref pointer requires the type that is held inside of it to inherit from ref counted or ref counted thread safe. Shared pointer doesn't require this. Why? So shared putter sticks an allocation and beside your object and then puts your object here. So it's the ref count is externalized to your object being stored and owned by the shared pointer. Chromium took this position to do intrusive ref counting. So because we inherit from a known type, we stick the ref count in that base class, ref counted or ref counted thread safe. And so that is enforced by the compiler. You must inherit from one of these two in order to be stored and owned in a scoped ref putter. What's the difference? Ref counted is the default choice, but it's not thread safe. So the ref counting is cheap. It's the more performant one. But if you have a scoped ref putter on two different threads owning the same object, their ref counting will race, can be wrong, and you can end up with a double free, which is another way that pointers can go wrong, two things freeing the same thing. Or you could end up with potentially not freeing it at all, probably. I guess I've never checked if that's possible. But they can race, and then bad things happen. Whereas ref counted thread safe gives you atomic ref counting. So atomic means that across all threads, they're all going to have the same view of the state. And so it can be used across threads and be owned across threads. And the tricky part there is the last thread that owns that object is where it's going to be destroyed. So if your object's destructor does things that you expect to happen on a specific thread, you have to be super, super careful that you synchronize which thread that last reference is going away on, or it could explode in a really flaky way.
So this sounds useful in other ways, right? So what are some kind of more design things to consider in terms of when a scoped ref pointer is useful and does help enforce maybe things that you want to enforce, like relative lifetimes of certain objects?
Right. So generally, we kind of recommend that you don't use ref counting if you can help it. And that's because it's hard to understand when it's going to be destroyed. Like I kind of alluded to with the thread situation, even in a single thread situation, how do you know which one is the last reference? And is this object going to outlive that other object? Maybe sometimes. It's not like super obvious. The way it's a little more clear with a unique putter, at least local to where that unique putter's destruction is. But there's usually no scoped ref putter. You can say, this is the last one, so I know it's gone after this thing's gone. Like, maybe it is, maybe it's not often, right? So it's a bit tricky. However, there are scenarios when you truly want, like a bunch of things to have access to a piece of data, and you want that data to go away when nobody needs it anymore. And so that is your use case for a scoped ref putter. It is, nicer when that thing being with shared ownership is, not doing a lot of interesting things, especially in its destructor, because of the complexity that's involved in shared ownership. But, you're welcome to shoot yourself in the foot, I guess, with this one, if you need to.
We're hoping to help people not shoot themselves in the foot, so,
Yes.
Use scoped ref pointer carefully is the lesson
Yeah.
there. So you mentioned shared pointer. Is that something we see much of in Chrome, or is that something that we generally try to avoid in terms of things from the standard library?
That is something that is banned in Chrome, and that's just basically because we already have scoped ref putter, and we don't want two of the same thing. There's been various times where people have brought up, why do we need to have both? Can we just use shared putter now? And nobody's ever done the kind of analysis needed to make that kind of decision, and so we stay with what we're at.
If you want to do that, there's someone that'll tell you what to do. So something that when I was using scoped ref pointer, I came across that you need a weak pointer factory to create such a pointer. So weak pointers and weak pointer factories are one of those things that you see a lot in Chrome and are one of these base things. So tell us a bit about weak pointers and their factories.
Absolutely. Okay, so weak pointer and weak pointer factory have a bit of an interesting history. Their major purpose is for asynchronous work. Chrome is basically a large asynchronous machine, And what does that mean? It means that like we break all of the work of Chrome up into small pieces of work, and like every time you're like done a piece, you go and say, okay, I'm done, and when the next piece is ready, run this thing, right? And maybe that next thing is like a user input event, maybe that's a reply from the network, whatever it might be, right? And there's just a ton of steps in things that happen in Chrome. Like in navigation has like a request, a response, maybe another request, some redirects, whatever, right? That's an example of like tons of smaller asynchronous tasks that all happen independently. So what goes wrong with asynchronous tasks? You don't have a continuous stack frame. What does that mean? So like if you're just running some synchronous code, you make a variable, you go off and you do some things, you come back, your variable's still here, right? You're in this stack frame and you can keep using it. You have asynchronous tasks. Okay, you make a variable, you go and do some work, and you are done your task. Boop, your stack's gone. You come back later, you're going to continue. You don't have your variable anymore. So any state that you want to like keep across your various tasks has to be stored and like what we call bound in with that task. So if that's a pointer, that's especially risky, right? So we talked earlier about use after freeze. Well, you can, I hope, imagine how easy it is to stick a pointer into your state, be like, okay, this pointer is valid, I'm using it, okay, I go away. I come back when? I don't know, sometime in the future, and I'm going to go use this pointer. Is it still around? I don't own it, right? I didn't use a nuke pointer. So, like, who owns it? How do they know that I have a task waiting to use it? Well, unless we have some side channel communicating that, they don't. And how do I know if they've destroyed it? If we don't have some side channel communicating that, I don't know. And so I'm just going to use this pointer and, bad things happen. Your bank account's gone. So.
No, my bank account.
Yeah, I know. So what's the side channel? The side channel that we have is weak pointer. So weak pointer and weak pointer factory provide this communication mechanism where weak pointer factory watches an object, and when the object gets destroyed, the weak pointer factory inside of it is destroyed, and that sets this little bit that says, I'm gone. And then when your asynchronous task comes back with its pointer, but it's a weak pointer inside of it, and tries to run, it can be like, am I still here? If the weak pointer factory was destroyed, no, I'm not. And then like, well, I don't know, you have a choice of what to do at that point. Typically, we're just like, okay, abandon ship, don't do anything here. This whole task is aborted. But maybe you do something more subtle. That's totally possible.
Okay. So I think the example I actually meant to say that uses a weak factor is a safe ref, which is another base type. So yes. Tell us a bit about safe refs.
Yes. Okay. So weak pointer is cool because of the side channel that you can examine, right? So you can say like, are you still alive to your object? And it can tell you like, no, it's gone, or yeah, it's here. And then you can use it. The problem with this is that in places where you as the code author want to believe that this object is actually always there, but you don't want a security bug if you're wrong, right? And it doesn't mean that you're wrong now even. Sometime later, someone can change code unrelated to where this is, where the ownership happens, and break you. And maybe they don't know all the users of a given object and changing its lifetime in some subtle way, maybe not even realizing they are. Suddenly you're introducing security bugs. And so that's why native pointers can be pretty scary. And so saferef is something we can use instead of a native pointer to protect you against this type of bug. It's built on top of weak pointer and weak pointer factory. That's its relationship, but its purpose is not the same. Right? Okay, so what saferef does, what saferef does is it says safe putter?
Safe ref.
Putter. Safe ref.
I think there's also a safe pointer, but
yeah. We were going to add it. I'm not sure if it's there yet. But so two differences between safe ref and weak putter then, right? Ref versus putter, it can't be null. So it's like a reference wrapper. But the other difference is you can't observe whether the object is actually alive or not. So it has the side channel, but it doesn't show it to you. Now, why would you want that, right? If the information is there anyway, why wouldn't you want to expose it? And the reason is because you are documenting that you as the author understand and expect that this pointer is always valid at this time. So it turns out it's not valid. What do you do? If it's a weak pointer, people will tend to say, oh, we don't know if it's valid, it's a weak pointer. Let's check. Am I valid? And if I'm not, return. And what does that result in? It results in adding a branch to your code. You do that over and over and over and over, and static analysis, which is what we as humans have to do, we're not running the program, we're reading the code, can't really tell what will happen because there's so many things that could happen. We could exit here, we could exit there, we could exit here, like, who knows, right? And that makes it increasingly hard to maintain and refactor the code. So SafeRef gives you the option to say, this is always going to be valid, you can't check it, so if it's not valid, go fix that bug somewhere else. It should be valid here.
So what kind of...
The assumption's broken.
So what kind of errors happen when that assumption's broken? Is that a crash? Is that a decheck kind of thing?
For SafeRef and for weak pointer, if you try to use it without checking it or write it incorrectly, they will crash. And crashing in this case means a safe crash. It's not going to lead to a security bug. It's literally just terminating the program.
Does that also mean you get a sad tab as a user, like when the little sad file comes up?
Yep.
All right.
Yes, it would. If you're in the renderer process, you take it down, it's a sad tab. So that's not great. It's better than a security bug, right? Because like your options here are don't write bugs. Ideal. I love that idea, but we know that bugs happen. Use a native pointer. Security problem. Use a weak pointer. Okay, that makes sense if you want it to, sometimes not be there. But if you want it to always be there, because you have to make a choice now of like what you're supposed to do if it's not, and it makes the code very hard to understand. And you're only going to find out it can't be there through a crash anyhow, right? Or use a SafeRef, and it's going to just give you the option to crash. You're going to figure out what's wrong and make it no longer do that.
Yeah, I think wanting to guarantee the lifetime of some other things is like a pretty common thing that you might come across. So I'm sure there are many cases for many people to be adding SafeRefs to make their code a bit safer and also ensure that if something does go wrong, it's not leading to a memory bug that could be exploited in who knows how long, because we don't always hear about those, right? If it crashes and it can reliably crash, at least it's there, you can fix it. If it's not, we're hoping that one of our VRP vulnerability researchers find it and report it, but that doesn't always happen. So if we can know about these things, that's good. Okay, so another new type in base that people might have been seeing recently is a raw_PTR, which is maybe why earlier we were saying let's call them native pointers, not raw pointers, because the difference between a raw_PTR and raw pointer, very easy to mix those up. So why don't you tell us a bit about raw_PTRs?
Yeah. Okay. So raw pointer is really cool. It's a non-owning smart pointer. So that's kind of like weak pointer or SafeRef. These are also non-owning, and it's actually very similar in inspiration to like what weak pointer is. So it has a side channel where it can see if the thing it's pointing to is like alive or gone, right? So for weak pointer, it talks to the weak pointer factory and says like, am I deleted? And for raw pointer, what it does is it keeps a reference count, kind of like scoped ref pointer, but it's a weak reference count. It's not owning, and it keeps this reference count in the memory allocator. So Chrome has its own memory allocator for new and delete called partition alloc, and that lets us do some interesting stuff. And this is one of them. And so what happens is, as long as there is a raw pointer around, this reference count is non-zero. So even if you go and you delete the object, the allocator knows there's some pointer to it still out there, and so it doesn't free it. It holds it. and it poisons the memory. So that just means it's going to write like some bit pattern over it. So it's not really like useful anymore. It's basically reinitialized the memory. And so later, if you go and use this raw putter, you get access to just like dead memory. It's there, but like it's not useful anymore. You're not going to be able to create security bugs in the same way. Because like when we first started talking about a use after free, right? You have your goat, you free it, a cow is there, and now your pointer's pointing at the wrong thing. You can't do that because as long as there's this raw putter to your goat, the goat can be gone, but it's nothing else is going to come back here. This is still taken by that like poisoned memory until all the raw putters are gone. So that's their job, is to like protect us from a use after free being exploitable. It doesn't necessarily crash when you use it incorrectly. You just get to use this bad memory inside of it. If you try to use it as a pointer and then you're using a bad pointer, you're going to probably crash. But it's a little bit different than a weak pointer, which is going to like deterministically crash as soon as you try to use it when it's gone, right? It's really just a protection or a mitigation against security exploits through use after free. And then we recently just added raw ref, which is really the same as raw putter, except addressing nullability. So smart pointers in C++ have historically all allowed a null state, right? And so that's representative of what native pointers did in C, right, and C++. And so this is like kind of just bringing this along in this kind of like obvious historical way. But if you look at other languages that have been able to like, you know, break with history and make their own choices kind of fresh, we see that they make choices like not having null pointers, right? Not having null smart pointers. And that increases the readability and the understanding of your code greatly. So just like for weak pointer, how we said, oh, well, we just check if it's there or not, and if it's not, we return and so on, right? It means every time you have a weak pointer, you have like, if you're thinking of like a timeline, right? Every time you touch a weak pointer, you're like, your timeline splits. And so like you get this like exponential timeline of possible states that your software is in. That's really intense, right? Whereas every time you can not do that, say this can't be null. So instead of weak pointer, you're using saferef. This can't be not here, or null actually, right? Weak pointer can just be straight up null. This is always present. Then you don't have a split in your timeline, and that makes it a lot easier to understand what your software is doing. And so for raw putter, it followed this historical precedent. It lets you have a null value inside of it, and raw ref is our like kind of like modern answer to this, you know, new take on nullability. And so raw ref is a reference wrapper, meaning it holds a reference inside of it conceptually, meaning it just can't be null. This is just basically it. It's a pointer, but it can't be null.
So these do sound like the most straightforward to use. So basically, if you're not sure, for your class members at least, right? Anytime you have you would use a native pointer or an ampersand, basically you should always just put those in either a raw putter or a raw ref. Is that right?
Yeah, that's what our style guide recommends. With one nuance. So because raw putter and raw ref interact with the memory allocator, they have the ability to be like turned on or off dynamically at runtime. And there's a performance hit on keeping this reference count around. And so at the moment, they are not turned on in the renderer process, because it's a really performance critical place. And the impact of security bugs there is a little less than in the browser process, where you just immediately get access to the whole, you know, system. And so we're working on turning it on there. But if you're writing code that's only in the renderer process, then there's no point to use it, and we don't recommend that you use it. But the default rule is yes, don't use a native pointer, don't use a native reference as a field to an object. Use a raw putter, use a raw ref. Prefer raw ref, right? Prefer something with less states, always, because you get less branches in your timeline. And then you can make it const if you don't want it to be able to be rebound to a new object. right? If you don't want the pointer to change. Or you can make it mutable if you want it to be able to.
Okay, very cool. So you did mention that these types are ref counted, but earlier you said that you should avoid ref counting things. So
yes,
what's the balance there? Is it because with like a scope ref pointer, you're a bit more involved in the ref counting, or is it just this is like, okay, we've done it for you, you can use it, this is okay?
No, this is a really good question. Thank you for asking that. So there's two kinds of ref counts going on here. I tried to kind of allude to it, but it's great to make it clear. So scope ref putter is a strong ref count, meaning the ref count owns the object. So the destructor runs, the object is gone and deleted when that ref count goes to 0. Raw ref and raw pointer are a weak ref count. They could be pointing to something owned in a scope ref putter even. So they can exist at the same time. You can have both kind of ref counts going at the same time. A weak ref count, in this case, is holding the memory alive so that it doesn't get reused, but it's not keeping the object in that memory alive. And so from a programming state point of view, the weak refs don't matter. They're helping protect you from security bugs. They're helping to make, when things go wrong, when a bug happens, they're helping to make it less impactful. But they don't change your program in a visible way. Whereas strong references do, right? That destructor's timing is based on when the ref count goes to 0 for a strong reference. So that's the difference between these two.
So when you say don't use ref counting, you mean don't use strong ref counting?
I do.
Cool.
Yes.
Yeah, and if you want to learn more about the raw pointer, raw putter, raw ref, that's all part of the Miracle Pointer project, and there's a talk about that from BlinkOn. I'll link that below also. Right, so in terms of other base types, there's a new one that's called base expected. I haven't even really seen this around, so can you tell us a bit more about how we use that and what that's for?
Yeah, so base expected is a backport from C++ 23, I want to say. So the proposal for base expected actually cites a Rust type as inspiration, which is called stood result in Rust. And it's a lot like option, right? So it's used for return values, and it's more or less kind of like a replacement for exceptions. So Chrome doesn't compile with exceptions enabled even, so we've never relied on exceptions to report errors, but we have to do complicated things like with option to return a bool or an enum, and then like maybe some value. And so this kind of compresses all that down into a single type, but it's got more state than just an option. So expected gives you two choices. It either returns your value, like option can, or it returns an error. And so that's the difference between option and expected. You can give a full error type. And so this is really useful when you want to like give more context on what went wrong or why you're not returning the value. So it makes a lot of sense in stuff like file I/O, right? So you're opening a file and it can fail for like various reasons, like I don't have permission, it doesn't exist, whatever, right? And so in that case, the way you would express that in a modern way would be to return base expected of your file handle or file class, right? And as an error, some enumerator perhaps, or even an object that has additional state beyond just like I couldn't open the file, but maybe a string about why you couldn't open the file, or something like this, right? And so it gives you a way to return a structured error result.
That sounds useful in lots of cases, for sure.
Yeah.
So all of these types are making up for basically what is lacking in C++, which is memory safety, right? C++, it does a lot, it's been around for a long time, most of Chrome is written in it, but there are all these memory issues, and a lot of our security bugs are a result of this. So you're working on bringing Rust to Chromium. Why is that a good next step? Why does that solve these problems we're currently facing?
Right, so Rust has some very cool properties to it. Its first property that is really important to this conversation is the way that it handles pointers, which in Rust would be treated pretty much exclusively as references. And what Rust does is it requires you to tell the compiler the relationships between the lifetimes of your references. And the outcome of this additional knowledge to the compiler is memory safety. And so what does that mean? It means that you can't write a use after free bug in Rust unless you're going into the unsafe part of the language, which is like where scariness exists. But you don't need to go there to write a normal program, so we'll ignore it. And so what that means is, right, you can't write that bug. And so that doesn't just mean like, like I also, like to believe I can write C++ without a bug. That's not true. But I would like to believe that. But it means that like later when I come back and refactor my code, or someone comes who's never seen this before and fixes some random bug somewhere related to it, they can't introduce a use after free either. Because if they do, the compiler's like, hey, it's going to outlive it. You can't use it. Sorry. And so like there's this whole class of bugs that you never have to debug, you never ship, they never affect users. And so this is like a really nice promise, right? Really appealing for a piece of software like Chrome, where our basic, like purpose is to handle arbitrary and adversarial data, right? You want to be able to go on some web page. Maybe it's hostile, maybe not. You just get a link, right? You want to be able to click that link and trust that even if it's like really hostile and wanting to destroy you, it can't, right? Chrome is that like safety net for you. And so Rust is that kind of like safety net for our code to say like, no matter how you change it over time, it's got your back. Like you can't introduce this kind of bug.
Yeah, that sounds great. So this Rust project sounds really cool. If people want to learn more or get involved, right? If you're into the whole languages, memory safety kind of thing, where can people go to learn more?
Yeah, so if you're interested in helping out with our Rust experiment, then you can look for us in the Rust channel on Slack. If you're interested in C++ language stuff, you can find us in the CXX channel on Slack as well as the same CXX at chromium.org mailing list. And there is, of course, the rust-dev at chromium.org mailing list if you want to use email to reach us as well.
All right, very cool. Thank you very much, Dana. There will be notes from all of this also linked in the description box. And thank you very much for this first episode.
Yay! Thanks, Sharon. This was fun.